All right, let's just jump right into this explainer. Today, we're looking at some absolutely fantastic insights from Lecture 29 by Skip Uni. We are tackling something that is literally at the core of programming, and that is the call stack in C++. So if you have ever found yourself wondering exactly how functions execute in C++, well, you are definitely in the right place. We're going to explore the function call stack together, step by step, and really figure out how stack frames in C++ operate right there beneath the surface of your code. You know, what's really interesting about this whole concept is how it leads us into this almost invisible mystery. Think about it for a second. You write a program with, say, 2, 3, or maybe even dozens of functions. How on earth does your computer track all those running functions and their specific variables without just getting hopelessly confused? Like, how does it actually know where to pause, where to jump next, and then exactly how to get back to where it started? To figure that out, we're going to walk through this complex journey together today. Here is our quick roadmap. First, we'll hit memory basics in C++. Then, the anatomy of stack frames. Third, a step-by-step look at the call stack itself. Fourth, the LIFO popping process. And finally, how to use all this knowledge to completely ace your technical interview.
Let's kick things off with Section 1, Memory Basics in C++, specifically looking at the stack versus the heap.
Okay, so the absolutely crucial point before we can even begin to understand function execution is defining exactly where these functions actually live inside the computer. And this brings us to the core division in C++ memory management. On one side, we've got stack memory, and on the other, heap memory. Now, heap memory is dynamic. It's used at runtime when you need to increase or decrease your memory allocation on the fly. We'll leave that for another day, though, because what we are hyper-focused on right now is the stack memory. Stack memory is static. Its size is totally fixed and known right at compile time. The biggest thing to remember here is that our functions operate strictly within this static space of the stack. They don't touch the heap for this, they only use the stack. Moving right along to Section 2, the anatomy of stack frames and what's actually inside the record. So let's zoom in on the specific memory blocks that get created inside that stack memory we just talked about. Whenever a function is called in your program, the system instantly creates a dedicated block just for it. We call this block a stack frame or an activation record. Think of it like a personalized little workstation for that specific function call. And it holds 4 very specific pieces of information. First up, it tracks the name of the called function itself. Second, it holds any parameters that got passed into that function. Third, it stores the function's local variables. And fourth, and guys, this one is wildly important, it stores a return address. This return address basically acts as a map for the control flow. It literally tells the computer exactly where to go back to once the function finishes its job. Which brings us to Section 3, a step-by-step look at the call stack and actual function execution. This is the core journey right here, where we translate these abstract concepts into a real visual execution. I want you to think of this whole process like stacking physical plates in a cafeteria. Execution in C++ always, and I mean always, starts at the very bottom with the main function. As soon as execution begins, boom, a stack frame for main is placed right at the bottom. Then, let's say main calls function 1. The control flow jumps over, and a brand new stack frame for function 1 is generated and placed directly on top of the main frame. Next up, function 1 calls function 2. Instantly, a third stack frame is created for function 2 and placed right on top of function 1. So as you can see, the stack is literally building upward, layer by layer, with every single new function call. Now it's super fascinating to track the actual data flowing through those stacked plates. Down at the bottom in our main function, let's say we have 2 local variables, num1 set to 10 and num2 set to 20. When main calls function 1, it passes those exact values up. So inside the stack frame for function 1, those values map to its parameters. Let's call them a and b. So a becomes 10 and b becomes 20. Function 1 then does a little math, adds them together, and stores the result in a local variable called sum, which obviously equals 30. Finally, function 1 calls function 2 and passes that sum upwards. So in the top stack frame for function 2, it receives a parameter called result, holding the value of 30. This perfectly shows how data travels securely up the stack from one frame to the next. All right, Section 4, the LIFO popping process, or last in, first out. So once that top function finishes its job, say by printing a result to the screen, the lifecycle enters the tear down phase. But before we start tearing things down, we absolutely must define the golden rule of stock memory, which is LIFO, last in, first out.
This is a strict, unbreakable operational principle where whatever data goes into the memory last will be the very first thing to come out. Remember our stack of cafeteria plates? The last plate we put on the very top of the stack is the first one we have to grab. You can't just yank a plate from the bottom or the whole thing crashes.
Let's actually apply LIFO to our program now. Function 2 finishes printing its result. It has reached the end of its code. Because of the LIFO rule, that topmost stack frame for function 2 is popped first. And when we say popped, it simply means the frame is destroyed and completely removed from memory. Now remember that return address we talked about a minute ago? Well, the control flow looks at the return address stored in function 2's frame right before it's destroyed, and it uses it to seamlessly drop back down into function 1. Okay, so now we are back in function 1. The control flow looks around and realizes, hey, there are no more lines of code to execute here either. Its job is completely done. So following that exact same LIFO rule, the function 1 frame is also popped. It gets completely cleared out from memory. And once again, it checks its return address, which sends the control flow right back down to where we started.
And of course, that starting point is main. The control flow followed the return address straight back down. Once main finishes up any remaining final lines of code, its frame is popped as well. So now, the stack memory is left completely empty, all the resources are freed up, and the program safely and successfully terminates. Honestly, it is incredibly elegant when you see the whole lifecycle laid out like this.
Finally, let's hit section 5, acing your technical interview and standing out to employers. You might be wondering, why does all this granular, step-by-step tearing down and building up actually matter for you? Well, as highlighted in Lecture 29, being able to clearly verbalize this exact lifecycle is a game changer. Whether you're sitting across from a tough technical interviewer, taking university exams, or doing competitive programming, they really want to know that you understand what happens beneath the surface of your code. If you can confidently explain these stack frames, talk about activation records, and trace that LIFO popping process just like we did today, you are absolutely going to stand out from the crowd. To wrap up this explainer today, I want to leave you with a bit of a provocative thought. What do you think would happen to this delicate stock process if a function just kept calling itself endlessly without ever hitting a return? Imagine stocking those plates higher and higher, forever, into a static, fixed-size space. I'll let you ponder the explosive consequences of infinite recursion as you continue exploring the fascinating mechanics of C++. Thanks so much for hanging out and learning with me today.